All right, this is going to be the pre-lab video for experiment number 34. Because we're looking at the oxidation and reduction reactions. And we're looking specifically for the electron transfer. So we're not going to be measuring voltages, we're not going to be looking at potentials or electrolysis amounts. What we're really going to be looking at is trying to identify the electrons being transferred, and then we're going to look at oxidation and reduction reactions. So before you start the lab with its data, we do want to work through this first part. So this is that consider this prior to the lab. And so they start off with a couple different examples. And so one of the ones that we're going to look at is we're going to look at example number 1. So this is the chart where it has 2 aluminum as a solid plus 3 chlorine gases going to 2 aluminum, 3 plus, and 6 chloride ions. And so it asks us to do 3 things. We want to write down the reducing agent. We want to write down the oxidizing agent. We then want to talk about who oxidized. We want to talk about the oxidation number increase, reduced, and the oxidation number decrease. So looking at this one, we know that elements in their elemental state are 0 for the oxidation states. The ions, they should match their ions. So this is a +3, this is a -1. And so our chlorine has gone through a change from 0 to -1. So that means that it's reduced. So that's the element that's reduced. It's decreased by -1, or you can just write 1, either one of those. On the other side, our aluminum, it's lost 3 electrons, so it's increased in its oxidation number by 3, and so it's oxidized, right? And so remember that oxidizing is losing electrons. Losing electrons oxidized, Leo the lion, right? And so we have our elements that have oxidized, we have the ones that are reduced, we know their amounts. Oh, I managed to erase our -1, and our +3. And so the only other thing that we have left to do is identify our reducing agent and our oxidizing agent. So reducing agent makes things reduce, which means they oxidize. So a reducing agent in this case is our aluminum. Oh, that is a B, not an R. On the other side, oxidizing agents, they make things oxidize, and so they reduce. So for this example, our oxidizing agent should be our chlorine. Right? And so that's what we need to do for that first table as we work our way through. We'll do another one. Let's look down and we'll look at something with some compounds. So we're going to look a little bit more complicated. We're going to take 3 Na2CO3, Na2O2s, sorry, so used to carbonates. Na2O2 plus chromate Cr2O3 and our water, and we're going to 6Na plus 2CrO4 minus plus 2 hydroxides minus. So as I go through, I generally start with the ones that I know for sure and then work my way back from there. So that way, if there's something that gives me a problem, I don't have to jump around right to it. So this sodium, I know this one's going to be a +1 because it's an ion. I know that also for my hydroxide, my hydrogen is going to be a +1 And my oxygen is going to be a -2, and that will work itself out. My chromate, if each of those oxygens is a -2, then that means my chromium has to be a +6, right? 4 of these out of -2 is -8. We got a -2 charge, so my chromium has to be a +6. So that has worked out. Oxygen in the water, -2, +1. Now for my my chromate oxide, or my chromium oxide, there we go. If we assume that's a -2, then each of my chromiums have to be a +3. And then this becomes my last tricky one. So normally we would say that our oxygen should be a -2, which makes each of these sodiums a +2. But sodium really can't have a +2. So instead, our sodium can only ever be a +1. It's only got 1 electron to give away. And so that means that this is a unique case where our oxygen is in what we call the peroxide form. So now when we look through, we want to identify our reducer. So we have changes in our oxygen. Oh, that's not the oxygen. -1 to -2, so it's reducing by 1 electron. And we have our chromium, +3 to +6, right? So it's losing 3 electrons. So if we wanted to go through and identify, our reducing agent is going to be our Cr2O3, because it's the one reducing, or it's the one oxidizing, allowing the oxygen and the Na2O2 to reduce. This is going to be our oxidizing agent. And then our oxidizing is going to be our Cr, and it's going through a change of 3. Our reducing is going to be our oxygen. It's going through a change of 1. You can have -1 and a +3. That's fine as well. And so that's what we're doing on that first part. So we should be able to do that for the rest of them. So you want to go ahead and fill out that chart. The second part that we're going to look at is how we create redox tables. Now for redox tables, there's a couple of different ways for us to compare against them. Now, one thing that we're going to be looking at is we're going to look at our redox reaction. So let's look at our copper 2+ and our copper. So we can write these all in the same way. Right? We can either write them as reducing or oxidizing. And in general, we're going to write them as a reducing table. Right? What that means is at the top, inside of our box, the top left is going to be our strongest reducing agent, or sorry, our strongest oxidizing agent. While our bottom one is going to be our strongest reducing agent. So when they arrange themselves, whoever's on the top is going to arrange itself to be going to the reduction process. Whoever's on the bottom is going to rearrange themselves to go through the oxidizing process. So if we look at that first example, let's say that we have our copper 2+ and we're comparing it against our zinc 2+ to zinc. Let's say that when we put our zinc in solution and we put a piece of copper inside, if there's no reaction, we know that they have lined themselves up correctly, that we would have zinc 2+ and our copper is solid. If we had copper, or sorry, if we did that same thing with the zinc 2+, and this time there was a reaction, zinc came out, right? So that means that zinc solid formed on our copper, then that means that our zinc preferred to be a solid and the copper was in its ions. So when we want to compare them, for this top one, its redox table looks like our copper 2+ goes to copper is better than our zinc 2+ going to our zinc, right? We would prefer for this top one to be going in that way to make our copper solid, while our bottom one should remain as our ions. Now, our bottom chart, what this one looks like is that our zinc 2+ is a stronger reducing or oxidizing agent than our copper, because they swap places. When we put them in, our copper rearranged itself so that it could go through an oxidizing process, and our zinc rearranged itself so it could go through a reducing process. So whoever's the strongest oxidizing agent goes on the top left, whoever's the stronger reducing agent goes on to our bottom right. And so as we read through our lab, as we find and record the different data, then we're going to use that in order to create our redox tables and start to put those into place for us. Now, each of these pairings is called a couple, a redox couple. Because we're comparing their forward and their backward reaction of the ion going to the solid going to the ion. And once we have a chart where we can see which one reduces and which one oxidizes for all of them, then we can compare several different ones. Because if we have a third one that's coming in here, let's say that we have a solution, and inside that solution we have some aluminum plus. And we put that copper inside. And this time, instead of solid forming, we got no reaction. We can add that into our table. We know that because the aluminum wasn't a strong enough oxidizing agent to reduce our, or to oxidize our copper, we know that it has to go down below our copper. And so we can use the responses in order to track them. And so that's how we're going to make more and more complex reduction tables. And once we compare one of them against it, we can use that to fill in the other parts. Now for your data is going to come in a variety of ways today. It's going to come in through experimental videos that I found through YouTube. And then for some of them, we'll have the demonstration videos. But there'll also be explanations of what we should have seen in the data video. Yeah. Specifically, this one really starts to show up, not in part 1 or part 2, because I was able to find ones where they worked all the way through, but kind of in part 4 and part 5. We'll have to watch those videos. I wanted you to be able to see what a strong, what the experiment looks like, but I wasn't able to find something for every single test that you need to run. And so you're gonna wanna be looking at your, the YouTube videos and watch through the data ones. That way you can collect all your data that you need, right? You'll be able to work this one up, and then you'll be able to turn in your data sheet or your worksheet just like usual. So we're turning in through Gradescope as well. All right, very good.